his PhD back to 1990 in Utrecht University, which is now stopped to exist after 300 years history, which is a pity last year due to some administrative decision. This institute unfortunately stopped existing, but then Han was lucky to have his PhD there on radiative transfers, and he moved to Cambridge for 10 years, and now these days he's working in the United States in Sac Peak Observatory as a project scientist of the solar telescope, DST telescope there. So today we have a talk of Han on solar radiance modeling, which is one of his last publications, I think.
Can I? Yeah. So yes, can I turn this off? Okay. So let's see. Does it appear on the screen? Okay. So the discussion on climate change, Earth climate change, over the past decade has become probably one of the most contentious in science. And in part, the reason for that is the room left by the uncertainty in the contribution of the solar variations to the Earth climate. And to clarify that, here is a plot of the solar irradiance, the total radiation integrated over all wavelength that comes from the sun to the Earth in absolute units, about 1366 watts per square meter, and its variation with time. And you see clearly that there is an 11-year variation, which is the result of the appearance and disappearance of magnetic elements, what we call magnetic activity on the solar surface. And the variation due to this appearance and disappearance of these magnetic elements is about 1/10%. Depending a little bit on how you average, you see that the yellow signal is much more time dependent than the proxies that are also plotted here. One of the proxies of solar magnetic activity is, for instance, the blue line, the sunspot number, which of course is known for a long time because people have been able to see sunspots for hundreds of years already and have been able to count them. But this relation is not exact. So one of the problems that Earth climate modelers face is to characterize the exact solar radiation over a much longer time span for us to be able to separate, for instance, what is the influence of human activity on the climate from that of the solar variation. We need to know exactly what in ancient times, or at least over the last few hundred years, was the solar radiation input. And this is part of the exercise and part of characterizing this total solar irradiance over time is part of what I would like to talk about. Solar radiation variation does matter. For instance, this is a plot over a much longer time period, and in blue you see again the 11-year cycle, the coming and going of magnetic activity on the solar surface. And in red you see that there was, at the end of the 17th century, a strong minimum in this activity. And with that minimum was associated a time when there was a mini ice age, when the temperatures and in the solar or in the Earth, on Earth, were very much lower for a period of about 50 years. And you probably have all seen the pictures of people skating on the canals in the Netherlands in summer, which doesn't even happen in winter nowadays, sometimes. So there is a clear indication that the variations of solar irradiance and solar magnetic activity has an influence on the Earth climate. Of course, it is very difficult to measure this variation, because parts of the spectrum are strongly absorbed by the Earth atmosphere, which in red here is drawn how the radiation levels are observed as a function of wavelength on the Earth's surface, while in yellow here is drawn the spectrum as it is seen outside the Earth atmosphere. So clearly to accurately observe the solar irradiance spectrum, we need to observe outside the outside the Earth atmosphere. And for this, we need satellites, and satellites have only been around for the last couple of decades. So again, the problem is, how do we extend the knowledge of the solar irradiation further back in time? Now, let's see if this works. Yes. And yes. Of course, as I said, the solar atmosphere is not just an homogeneous big ball of gas. It has activity, and this magnetic activity causes all kinds of variation of the intensity. Moreover, the solar surface is also the granulation, the little bright regions that you see is also very time dependent. And the question is, can we characterize this structure of the solar atmosphere well enough that once we have an image of the sun, we can reproduce the spectrum, not only at the wavelength that we observe, but also at ultraviolet wavelengths, which are very important for Earth climate modeling, because the ultraviolet radiation, especially between 200 and 300 nanometers, has influence on the chemistry of the upper layers of the Earth atmosphere. For instance, ozone, the ozone levels depend a lot, and this very much influences weather. Okay. So, an overview of what I will talk about. I will just briefly in 2 slides mention an aspect of radiative transfer that I will use later on. I will talk then about the dynamic 3-dimensional solar atmosphere and how we typically model this, and the approximations, the necessary approximations to make this a tractable problem that we have to take. Then I will talk about semi-empirical modeling, which is one of the approximations that has been used very widely, and which also has its problems. Then I will talk a little bit about nonlinear spectral averaging as one of the problems of dealing with a non-homogeneous atmosphere, and also the effect of dynamics when processes that determine the radiative transfer in the atmosphere are slower than the dynamic timescales on which the atmosphere changes. You also have problems, and you cannot use hydrostatic models. And then I will end with some conclusions. So first, 2 slides about radiative transfer. How do we determine the emergent radiation from a given plasma, and how do we extract physical properties from the observation of that radiation field? Well, we solve the equation of radiative transfer. This of course, is one of the most simple equations of differential equations that you can imagine, but all the details are hidden, in fact, in all the details of the atomic physics that you have to also solve to calculate the radiation field, to determine the absorption coefficient chi and the emission coefficient eta. So when light passes through the atmosphere, the change in that intensity over a stretch of S is minus what is absorbed, chi times I, the intensity, plus what is emitted into that direction that you are observing. And you can rewrite that defining the source function as the ratio of the emissivity over the absorption, and rewrite the equation of radiative transfer this way. Now here's an example of how the source function in a strong line, in this case one of the lines of ionized magnesium at 280 nanometers behaves. Deep in the atmosphere, in layers where there are a lot of collisions and where the density is high, the source function, which is drawn here in gray, behaves very much like the Planck function. We have what we call local thermodynamic equilibrium. The higher and the higher you get, collisional coupling becomes less effective, and the radiation field starts to matter. Now imagine that the source function, which is the ratio of emissivity over absorption, which is more or less for a strong line like this, the ratio proportional to the ratio of the upper level of the transition divided by the number population of the lower level. And once the radiation field starts to see the outside world, the radiation field falls below the Planck function. And now the upper level of this transition can no longer be maintained at the level that would be required for local conditions. And therefore the source function drops below the Planck function. And therefore we have an intensity which is not necessarily related to the local temperature, to the local conditions, but is also determined by a radiation field that comes from a different place in the atmosphere. And this is one of the effects that I will discuss, is that the source function in some cases, in especially higher up in the atmosphere, is determined by the radiation field that not only is determined by local conditions, but also comes from conditions in other places of the atmosphere. So, the solar atmosphere. Of course, the solar atmosphere, the solar photosphere and the chromosphere are highly complicated and structured and dynamic, and they are shaped by the interplay between hydrodynamics, magnetic field, and the flow of radiation. To properly understand these environments and model the spectrum, you would really need to do full three-dimensional radiation magnetohydrodynamics. And people are doing this nowadays. But it is very time-consuming, computer-intensive. To model the full disk-integrated spectrum, which is what you require if you want to predict, do solar spectral irradiance modeling, is of course not possible, nor will it be in the future. We will have to do some approximations because we cannot model in detail the whole solar disk like we do now for a very small section of the disk. And so far, for this modeling, to describe the irradiance, we have relied on semi-empirical hydrostatic modeling, and I will come back to that exactly what that means. And the question that I would like to pose here is that adequate? Again, well, this movie won't play, unfortunately, but this would be a little time movie of the solar granulation to just show the time dependence of the convection, even when there is very little magnetic field present. You see some evidence of magnetic fields here in these bright points in the G band, which is a band about 1 nanometer wide that has a lot of lines due to the CH molecule, and that provides therefore a very nice contrast of the temperature conditions in the atmosphere. And the question is, does all this time dependence and this structure, even when in the absence of magnetic field, does this matter for the modeling of the radiation field? It gets even worse once we go to higher layers. This is an image now of the solar surface taken in the light of one of the hydrogen lines, the H-alpha line. And it shows a layer that is well above, about 1,000 or 1,500 kilometers above the photosphere. And it shows that this layer is completely dominated in structure by the magnetic field. At higher layers, the dominant force becomes now the magnetic field and no longer the hydrodynamic forces that are due to convection. So how do we model this? Well, we can write down the equations of hydrodynamics, and for this exercise, I will just ignore the magnetic and electrical forces and just write down the hydrodynamic forces. We start with the equation of mass conservation, and we add the equation of momentum, saying that the changes in momentum are what is of a given parcel of gas, for instance, are what streams into the matter, the forces that act by pressure, the forces that act by gravity, and the forces that act by viscosity. And we have the equation of internal energy. That's saying that the changes in internal energy are what in a certain element are what streams into that. And the work that is provided by pressure and some radiative heating and cooling, viscous heating and cooling, and conductivity. In the end, when you do everything as well as you can, you should see something like this. Maybe not. Yes. Okay, so this is one of the things that I didn't have time to change. Well, what you would see here is a kind of a movie that Mats Carlsson created from a simulation, and it is it's like a flyover over the simulation. And what this was intended to show you is that the surface of optical depth unity, the surface at which the light reaches you, is not a flat surface. It's a surface that is very corrugated. It goes up and down by about 200 kilometers because of opacity differences in the hot granules where material flows up, and the cooler intergranular lanes where cold material, after radiatively cooling, flows down. So coming back to the equation, and in particular the momentum equation, how can we simplify our thoughts? Because if we need to do full MHD solution of all these equations, this is a very time-consuming process, especially if we have to take into account what are the radiative losses and the radiative gains. So in the approximation of very small velocities and large horizontal scales, so that only the vertical gradients survive, we can simplify the momentum equation very severely. The first term drops out, the second term drops out, and we only are left with the gradient of pressure balanced by gravity, by the divergence of gravity, or in this case only the vertical gradient of gravity. So under this approximation of small velocities and large horizontal scale, we get as a first approximation that the equation of hydrostatic equilibrium, where the weight of the gas is balanced by of a column of gas is balanced by the local pressure. Now, how is this used in irradiance modeling? The way it works is the following. You take an image of the solar disk, a full disk image, in a certain band, or maybe in certain bands of wavelength bands, and you try to assign different components to this image. For instance, you're able to recognize a sunspot. You recognize what we call magnetic network, what is here the green stuff, and you assign different hydrostatic models to all these components. These hydrostatic models then look like this. They have they almost coincide deep in the atmosphere. They go to a kind of a temperature minimum, a chromospheric plateau, and then a transition region where the temperature goes from about 7,000–8,000 degrees to eventually 1,000,000 degrees in the corona. And these models represent then reproduce more or less the spectrum of each of these elements that you characterized from the full disk image. And so this procedure then is used to predict the total solar irradiance and the variation of the solar irradiance given the filling factor of the different components on the solar disk. However, of course, this assumes that each of these elements lives by itself and that each of these elements can be represented by a static model. How accurate is that? And of course, these semi-empirical models are inversions of an observed spectrum, but it's usually typically a spatially and temporally average spectrum of a given solar region, and therefore you can call them multi-parameters fit to this spectrum. But the spectrum, or the model in this case, is a hydrostatic model, which is a severe limitation. And often in these models, sophisticated radiative transfer is used to solve the equation of state. This comes in addition to the equation of hydrostatic equilibrium, of course. But no further physical laws are implemented to explain the thermodynamic temperature. So there's no energy balance. It is really a semi-empirical model that tries to reconstruct a temperature on the basis of a hydrostatic model that matches the observed spectrum as well as possible. And the question is, again, can a time-dependent or spatially inhomogeneous atmosphere be represented as a series of such models? And I think the answer is actually a clear no. So what are some of the problems that we may face in this case? There's the nonlinear averaging of inhomogeneous or temporal variations. There may be lateral radiative transfer, and there may be physical processes on time scale that are longer than the dynamical time scale. And I will come back to each of these cases. So say that we take a hydrodynamic simulation. And the top panel here is a snapshot, or the intensity calculated from a snapshot, one instant in time of such a simulation. And the bottom panel is a vertical cross-section of this. You see here the granules and the intergranular lanes, which are cooler in temperature. And here is now the source function at a continuum wavelength. And drawn in blue is the optical depth unity for that wavelength. And the arrows indicate the direction of the radiation. And you see that there is significant, in these places where there is, where the intergranular lanes are, there is significant horizontal contribution of radiation. And therefore there is significant possibility of the source function being influenced not only by what is below it, but also what is beside it. However, first, let's have a look at how well you can represent a inhomogeneous atmosphere with a one-dimensional atmosphere that has the same exact average properties. Say the average temperature or temperature stratification as a function of density is exactly the same as the one-dimensional I will compare it to. So what I've plotted here is the surface of optical depth unity at a continuum wavelength. And if we assume that we have LTE, namely that the source function is given by the Planck function, and if we assume that the Eddington-Barbier relation, which tells you that the emergent intensity is approximately the source function at tau equal 1, then the average intensity over a surface is given by the average of the Planck function on optical depth unity. Now, if we assume that the temperature variations compared to the average temperature are small, so that we can develop this Planck function in terms of a Taylor expansion in the relative temperature variation, then the average Planck function is the Planck function at the average temperature, small t equals 0, plus the first order drops out because that's just the average temperature, plus variations of the second derivative of the Planck function. And you can show that this is always positive. So the average intensity from a surface like this is larger than the Planck function at the average temperature. I mean, it's very simple, but it's the nonlinearities that are part of the radiative processes make that you always get a larger intensity from an inhomogeneous atmosphere, even if the properties of that atmosphere on average are the same as the one-dimensional model that you compare it to. This means that if you plot as a function of center to limb, where the center of the disk is 1 and the limb is 0, mu is the cosine of the viewing angle. If you compare now the intensity that you get from a 3D inhomogeneous model with the intensity that you get from a one-dimensional model with exactly the same average temperature stratification, you get a higher intensity and you overestimate the temperature gradient if you would interpret the upper curve in terms of a one-dimensional temperature stratification. The same happens when you look at molecular concentrations. The topmost equation is the Saar-Boltzmann equation for molecular concentration of molecule NAB, which consists of molecules N and B. And N is the number densities, and T the temperature, K the Planck coefficient, the Planck constant, and M the mass of the molecule. And you can clearly see that, of course, the average molecular density is unequal to the density of the molecule at the average temperature, because this is just a nonlinear function of temperature. And indeed, when you do the calculation, and there are a lot of curves here, but just compare the first two that I mentioned there. The solid is the curve represents the concentration of the CO molecule in the average CO concentration as a function of the opacity at 500 nanometers in a snapshot of MHD simulation, and the 1D tau curve, which clearly has a lower concentration, is the CO concentration as a function of height in a one-dimensional model that has exactly the same temperature and density stratification as the average from the 3D model. So non-homogeneities make it difficult and the non-linearity that are part of the radiative transfer process make it difficult to represent a three-dimensional structured atmosphere. And the same holds for time dependence, by the way. To represent that with a one-dimensional atmosphere with the same average properties. Now we get to lateral radiative transfer. As an example, I would like to show you some of the properties of this line, which is one of the lines of ionized calcium in the solar atmosphere. It is really a line that is used for chromospheric diagnostics because it formed at about 1,000 kilometers above the photosphere. And it's also one of the lines, the best lines to use in attempts to measure the magnetic field in the solar chromosphere, which is a very hard problem. Again, here I draw a source function, and in the same way as the first source function that I showed, in the source function here at this wavelength, for instance, is drawn here in a gray line. Optical depth unity is here, optical depth 0.3 and 3 are here. So most of the intensity that you see, the emergent intensity, comes from about this region, according to the Eddington-Barbier relation. You can show that the source function is something like a parameter epsilon times b, be the Planck function, plus 1 minus epsilon j, the mean intensity j. And indeed, you see that the source function in this case is almost completely given by j because epsilon is very small. Now, if you have a magnetic, what we call a magnetic flux tube, is a kind of an abstraction of a magnetic concentration. This magnetic concentration contributes pressure proportional to the square of the magnetic field strength. So inside of this magnetic flux concentration, you have gas pressure plus magnetic pressure. Outside, you have only gas pressure because the magnetic field is small. This means that the gas pressure inside this magnetic flux concentration at a given geometrical height is typically smaller. This means also that densities are smaller. So what happens there is that because of this, what we call evacuation, there's radiation that goes from the denser outer atmosphere into the flux tube. And these arrows now indicate the flow of radiation. You can clearly see that there is a lot of influx of radiation here that travels all the way to these regions. And what happens there is that this radiation field, because the source function of the 8542 line now depends on the radiation field, this irradiation contributes to the level of the source function. And when the source function is higher, the emergent intensity will be higher. And so if you would interpret the radiation field, for instance, on the axis of the flux tube, and you would interpret that in terms of a temperature, not knowing about the three-dimensional structure of this flux tube, you would interpret this as a higher temperature than there actually is. And so this three-dimensional effect actually makes you makes the diagnosis of this temperature wrong. So if you would base your hydrostatic models on, say, the intensities that you get from the flux tube center and ones that you would get from regions outside the flux tube, you would make a wrong diagnosis of the temperature in the flux tube, because you would not have accounted for the irradiance from the sides that contribute to the rise of the source function, and therefore give you a false impression that the temperature is higher. And you can clearly see that. Now, this is a bit of a complicated picture, but horizontally, I've showed the wavelength through the line. So you see the spectral line. And vertically, I now show the distance along the flux tube. So the flux tube is in the center. And when we go back, when you look, for instance, like this, you see the exposed hot walls in the continuum, and that is what you see in the wings of the line. These are the flux tube walls. And then here you see that there is enhanced emission. It has nothing to do with the temperature rise, but that is really the result of the horizontal irradiation of into this flux tube. Okay, finally, getting to processes that are slower than dynamical timescale. And one of the most important processes that we have to worry about is the ionization of hydrogen. Unfortunately, again, this won't show. This is now a series of snapshots from a one-dimensional simulation performed by Carlson and Stein, where they started out with a radiative equilibrium model, put a piston at the bottom of the atmosphere, so they vary the pressure, and that generates sound waves that then travel upwards, because the densities in the atmosphere become lower and lower, and you have to conserve rho v squared. The density becomes lower, rho becomes lower, v squared grows, and you form shock waves. These shock waves then dissipate and heat the atmosphere. But they also affect very much the hydrogen ionization, and therefore the electron density. So what I show here in this plot is the temperature in solid and the electron density in dashed lines of the initial state in the thin lines, and the average state of such a hydrodynamic simulation in one dimension. And for comparison, in dotted lines are shown the values for one of these average semi-empirical models. And you see in particular, when you look at the thick dashed line, that there is a difference of a factor of about 6 in electron density from the initial state to the average state of the simulation. And the reason for that is the following. Well, first, this is to give you an impression of what are the fraction of ionization in a typical atmosphere, they vary from in the temperature minimum from about 10 minus 5, 10 minus 4, where all the electrons typically in the photosphere are the result from ionization of metals, not from hydrogen, to about 1 when you go to the transition region. And the process of hydrogen ionization is the following. Most of the ionization of hydrogen comes from in the chromosphere, in the region about from the temperature minimum at about 500 kilometers to 1500 kilometers above the photosphere. These are now the energy levels of hydrogen, and the thickness of the lines of the arrows here indicates the dominance of the rates between them. And so ionization in hydrogen comes mostly from the Balmer continuum, so ionizing with radiation from the first excited level to the continuum in this way, and then recombination, which is typically a three-body process because it involves the capture of an electron and then a second electron that takes away the energy, and therefore this process is very density sensitive. This recombination typically occurs to higher levels, and then step by step by photon emission to lower layers, to lower levels. Now, as I mentioned, the recombination, which is a three-body process, is very density sensitive. So when you look at the relaxation timescales, which are plotted here, these curves here, and they are for different approximations, but it's not so important. The main issue is that you look at the relaxation timescales, the fact that you recombine not instantaneously, but it takes some time for these electrons and this atom to meet each other and then recombine. This becomes slower and slower when the density drops off, and you can see that it reaches 100,000 seconds here. This is, of course, much and much longer than the dynamical timescales, which are typically of order of tens of seconds in the chromosphere. So what happens is that you have one of these shock waves that are generated by motions, for instance, by buffeting by granules. The sound wave travels up, forms in the shock wave, and instantaneously ionizes the hydrogen. However, hydrogen doesn't have time to readjust after the passing of the shock wave. When the temperature of the atmosphere cools down, when the temperature goes down again, it takes a long time for it to recombine. So the ionization equilibrium is not given by the temperature only. It's not given by Saar-Boltzmann anymore. It's really given by the dynamical evolution of the atmosphere. And you clearly see that here in this plot, where the ionization of hydrogen, relative ionization of hydrogen, so the log of the proton density over the total hydrogen density, is shown for different levels in the atmosphere, where the instantaneous value that would be predicted by Saar-Boltzmann is plotted by the dashed line, and the actual value in the simulation is plotted by the solid line. And you see that higher in the atmosphere, the ionization is almost constant. So the atmosphere has no time to do any hydrogen recombination after the passing of the shock waves. So the electron density is much more characteristic of the levels that are predicted by the instantaneous equilibrium at the top of the shock waves, rather than the average of the temperature. One more thing about time dependence. This is the result of a similar, actually of the same simulation, that shows that it's you have to be very careful what model you use to interpret an average spectrum. This is a bit of a complicated plot, but again, in a solid line here, the thick solid line is shown the average temperature from the simulation that I was talking about, the one-dimensional hydrodynamic simulation. The thin lines, upper and lower, are the maximum in temperature. So the temperature really, when these shock waves pass through, the temperature varies by quite a bit, by tens of thousands of degrees. The dot dashed line, the thin dot dashed line, is again the temperature stratification that you get from a one-dimensional hydrostatic model that represents exactly the same spectrum. That is one of the FAL models, the FAL A in this case. Now the thick dashed line is the temperature that you would predict if you would interpret the average spectrum from the simulation. So you let the simulation run. You calculate the spectrum at every time step. Then you take the temporal mean of that spectrum. And you would interpret that spectrum in terms of a one-dimensional hydrostatic model. This is the temperature that you would get from that interpretation. So you cannot use, so funnily enough, the temperature that you get from putting this spectrum in terms of interpreting the spectrum of a one-dimensional hydrostatic model has a chromospheric temperature rise, while the actual average temperature of this model has a monotonously decreasing temperature. So these are very different things, and they only differ by the way you interpret your spectrum. You cannot use, in this case, it is very dangerous to use a one-dimensional hydrostatic model. So in conclusion, effects of nonlinear spectral averaging, lateral radiative transfer, and hysteresis are not represented by semi-empirical hydrostatic models, but are important, of course, for the solar spectrum. The interpretation of the solar spectrum in terms of hydrostatic models misrepresents the physics of the solar atmosphere, and therefore puts at risk of mispredicting parts of the spectrum that are not used for the creation of such models. Which is exactly what you wish to achieve by using hydrostatic models to model the irradiance spectrum. But we really need to do much more modeling to understand what are we able to get away with, right? Clearly, one-dimensional hydrostatic models are not good enough, I would say, to do this kind of modeling. But also, clearly, we cannot do the full MHD solution for the whole disk. So we'll need to find some kind of something in the middle that is accurate enough, but also computationally feasible. So thank you.
Okay, thank you very much for your talk. So now there is time for questions.
Hans, no doubt that you have to understand the three-dimensional nature and the time variability of the solar atmosphere to predict properly the spectrum. But somehow you associate semi-empirical models with the hydrostatic equilibrium models that come out of the simulation. And I think that the semi-empirical models that people use to predict the spectrum actually do more than just the hydrostatic part, because somehow they hide all these uncertainties so that the resulting model is able to produce observed spectrum. That's the constraint. So even if from a physical point of view they might not be very realistic, if you want to have a good prediction, they are going to do it much better than the average models that come out of the simulations.
I only showed that the hydrostatic solution is a part of is an approximation that follows from the full equations. But I agree with you that there is a lot of sophisticated radiative transfer that goes into the models. What I'm trying to show is that interpreting your spectrum in that way is still dangerous, even though the spectrum is reproduced that way. You interpret you get the wrong physics. When you have the wrong physics at the bottom, you may misrepresent wavelengths that you haven't worried about initially when you constructed your models.
Some more questions?
So Hans, with empirical models, how big is the problem in the end? What I mean is the following: a magnetogram or a continuum of the sun associated to pixels.
Sorry, I cannot hear you.
You cannot hear me. Okay, so I want to know how big the problem is, right? Yes. In the sense that take a continuum image and associate to each pixel an empirical model.
Yes.
It's an empirical model, complexity for Umbra, for Planck, and the whole transfer with.
Yeah. So, well, that is one of the things that I think clearly needs to be. I mean, I've indicated a few processes that would worry me, but I cannot give you the number of this is how much percent they make a difference. But if you.
I am asking this because I think people are happy with that, and they try to do irradiance reconstructions for years with that, and they sort of feel they are doing it okay, right? Or is there a big problem?
I think there is a big. I think there is a big problem. And people don't realize that there is a big problem.
Okay, more questions?
No hands. Can you go back to the flux tube, please?
Yes.
Right. This image, thanks. Just one question. You're having an energy input inside the flux tube, right?
What?
You're having an energy input inside the flux tube because...
No, in this case, I actually constructed a kind of a semi-empirical two-dimensional model. So I only, the constraint is that I do have horizontal pressure balance everywhere, and that determines the magnetic field, the shape of the magnetic field. But the temperature is given by semi-empirical models in this case. And so it's a kind of a toy model to show that has some physical consistency to show what are the effects of a magnetic field concentration like this. You do get actual heating because of this irradiance that is not represented in this model. Yeah. But that comes on top of the false signal that you get from the raising of the source function.
Yeah, my question was about that. I mean, normally when people start thinking about the flux tubes and all this, they tend to neglect these contributions, or it's very rarely thing. And my question is, how important is this heat source? You want to say that? I mean, for modeling the structure of the flux tube and all this.
In the radiation MHD modeling, all these effects are taken into account, except that maybe not in the chromospheric line so much, but definitely the photospheric heating that comes from irradiance is taken into account because they do treat radiation.
But does
the point that I wanted to make is that if you interpret again the radiation field coming from a structure, inhomogeneous structure like this, you may misinterpret some of the radiation field as temperature.
That I understand, but what I mean is, if this is important enough to modify, for example, the magnetic structure. I mean, if this heating in the boundary,
it does. Yes.
Because from the other side, when we want to model the flux tube, we normally forgot this contribution. Yes. So probably we get something that is not as good as it could from the MHD point of view. We want to say that. So we definitely need to take into account this.
Yes.
Have you ever tried to run this in time? I mean, leave it.
No, this is really a static model. So,
because it will be interesting to see if this heating is enough, for example, to definitely modify or disrupt the tube.
So, is there any more question?
Coming back to the beginning of your talk, when you talk about the radiance variations, you put the emphasis in the 3D structure of the atmosphere, magnetic fields. But is this really the most the critical aspect of it, of the variations with time, or is it more global properties of the sun and the magnetic field?
I would say that maybe those are more important. Definitely, it is very unclear. For instance, what is a good proxy? Because the sunspot number is not a very accurate predictor of for instance, especially UV irradiance. So that is definitely a problem. What I want to draw the attention to is that there are definitely, and I think that the time dependence actually is probably a more severe problem, because most of the ultraviolet radiation comes from the chromosphere and is not used to create the semi-empirical models. So, and the ultraviolet radiation varies by much more than the total. It varies by 10, 20%. And so this time dependence of the ionization I think is really important because it really changes the ultraviolet part of the irradiance that is predicted by taking images in the visible. And so I think that needs much more consideration. And I think the horizontal irradiance is an interesting part that we definitely need to look more carefully at, but it's probably less important than this time dependence.
It's okay. Is there any more question? So if not, let's thank again our speaker.